We just spent a lot of time analyzing reflection and how mirrors work to reflect light. Let's look at the other side of light rays now. Refraction. Refraction is the bending of light as it moves from one medium to another. In our diagram, we see light traveling from water up into air, and the angle at which it's traveling changes once the light moves into the second medium. When light is in any medium besides a vacuum, its speed is less than the speed of light. The index of refraction measures the ratio of the speed of light, c, to the speed of light in that particular medium. So in our equation, n is the index of refraction, c is the speed of light in a vacuum, and v is the speed of light in the medium. As our light wave travels from water to air, its speed changes, which affects the angle at which it travels through the medium. For this situation, we're considering air to have the same properties as a vacuum, which means that light will travel at the speed of light, c, in air. For the MCAT, we can assume that nothing can travel greater than the speed of light. So the speed of our light in any medium other than air is going to be less than c. By definition, the index of refraction of a vacuum is 1. However, for all other materials, the index of refraction will be greater than 1, since c will always be greater than v. We can use these indices of refraction to help calculate the new angle of light after refraction. Snell's law quantifies the angle at which our light will be refracted as it changes mediums. Up at the top of the screen, we see the equation of Snell's law. The index of refraction of medium 1 times the sine of the angle to the normal that the light is traveling in medium 1 is equal to the index of refraction of medium 2 times the sine of the angle to the normal that the light is traveling in medium 2. So that's a bit wordy. Let's just look at our diagram to simplify things. Our light is traveling up to the top of the water at a certain angle, theta 1. Once the light encounters the change in medium, the theta changes as well, to give us theta 2. These angles are conventionally measured in relation to the normal, which is this dotted line in the middle of our screen. The normal is the line that is completely perpendicular to the surface of the boundary between the two materials. As a rule, when light travels from a medium with a higher index of refraction to a medium with a lower index of refraction, light will bend away from the normal, just like we see here in our diagram. Theta 2 is greater than theta 1 since we moved from water, which has a higher n, to air, which has a lower n. How about the opposite situation? Now we have light coming from the air and refracting into water. Our light is traveling from a low n to a high n, which we see causes our light to bend towards the normal. At a certain angle, light will no longer refract. This angle is known as the critical angle, the angle at which light is refracted at the boundary. We can calculate the critical angle if we know the two indices of refraction. Once we exceed the critical angle, we get total internal reflection. At first, we see that our light is refracted going from water to air, but once we get past that critical angle, there's no more refraction. At this point, we get only reflection. If you've ever been underwater in a pool and looked out towards the surface of the water, you notice that the bottom of the pool was reflected. You've already experienced total internal reflection. Okay, enough about total internal reflection. For refraction, the MCAT will use lenses to test your knowledge, so let's ensure you have a good understanding of what's going on when you put on a pair of glasses. The first type of lenses we'll look at are convex lenses. Convex lenses are converging systems, which means that they'll bring parallel light rays together. In contrast to the single focal point of mirrors, lenses have two focal points, since light can travel from either end to the other. On the left side, you can see how parallel light rays will be refracted at angles such that they pass through the focal point on the other side. The opposite is true as well. If the light originates at the focal point at one side, the light rays will be refracted such that they end up parallel on the opposite side. The second type of lenses is concave lenses. Concave lenses are diverging systems, which means that they'll cause light rays to split apart instead of converge. Just like convex lenses, concave lenses also have two focal points. The bottom left diagram shows that parallel light rays will be split apart once they pass through the lens, and the bottom right diagram shows the opposite effect. So, while these diagrams can look a bit confusing, the main takeaway here is that concave lenses cause light rays to diverge. Your college physics classes may have gone into further detail about the actual properties of the lenses themselves, but for the MCAT you can simplify things a bit. The main concept to know about lenses is that light is refracted twice as it passes from the air to the lens and then from the lens to the air. The good news is that you can use all the equations we've already worked with to analyze magnification, image distance, and all the other values that lenses produce. Later on in this video, we'll work through an example of how to use these equations for lenses. Just like mirrors, lenses have their own sign conventions you should know. Object distance is positive when the object is on the same side as the light source, and O is negative when the object is on the opposite side of the light source. This mainly comes into play when you're dealing with combinations of lenses, so the image of the first lens will become the object for the second lens. A positive image is when the image is on the opposite side from the light source. So a real image for a lens would be on the opposite side. A negative image is when the image is on the same side as the light source. You'll have a positive R value when the lens is convex and a negative R when the lens is concave. You'll have the same situation with focal length. And luckily, magnification sign conventions are the same as with mirrors. A positive magnification is an upright image, while a negative magnification is an inverted image. And just like I mentioned before, you can use the IR and UV mnemonic to remember whether an image is real or virtual based on its orientation. Let's try an example to incorporate all this information about lenses. Here, we are asked about the image produced by a converging lens. Of course, we need to draw a picture. Converging lens is another word for a convex lens. Our object is located between the focal point and the lens. We can use the same equation from earlier to calculate the image distance. We have a converging lens, which means our focal length is positive. So we didn't explicitly state this before, but the object distance for a single lens system will always be positive, since the object is the only source of light here. Let's rearrange our equation to solve for I, find the value of f, which is 20 centimeters, find the value of O, 10 centimeters, and solve. Our image distance is negative 20 centimeters. To determine whether the image is upright or inverted, we need to consider the magnification. Plugging our values in, we get a magnification of positive 2. A positive magnification indicates an upright image, just like with mirrors. To determine whether the image is real or virtual, we need to look at the sign of image distance. A negative image distance tells us that we have a virtual image, and for lenses, that image will be on the same side as the source of light. For lenses, we can draw ray diagrams too, and here we see that the image is farther away from the object, is upright, and is on the same side as the object, which means it's a virtual image, all confirming our previous deductions. In this situation, we took an object that was pretty close to the lens and produced an enlarged virtual image. This is exactly what happens when you use a magnifying glass to make an object look larger. Optometrists often describe a lens in terms of its power. In optics, power is measured in diopters and is calculated with this equation. Focal length needs to be in units of meters in order to properly calculate the power. Power will have the same sign as the focal length, so power will be positive for converging lenses and negative for diverging lenses. People who are farsighted need converging lenses to correct their vision, so they'll need a positive diopter prescription. In contrast, people who are nearsighted need diverging lenses and will therefore need a negative diopter prescription. One way the MCAT can complicate optics problems is through multiple lens systems. You can calculate the equivalent focal length with this equation and the power of a system with this equation. But it's important to note that these two equations are only for lenses that are in contact. Lenses that are in contact are a series of lenses with negligible distances between them, just like contact lenses, which are in contact with the lenses of your eyes. Lenses that are not in contact are much more complicated than lenses that are in contact, so you don't need to worry about calculating power or focal length for lenses not in contact. However, for any combination of lens system, regardless of whether the lenses are in contact or not, you can use this equation to calculate the magnification. We've finally reached the end of our content. Now it's your turn to try your hand at some practice questions. This first question asks you to select the true statement about an object in a convex mirror. Take a second and pick an answer. I hope you didn't spend your time with calculations here. If you remember from earlier, an object in any position in relation to a convex mirror will be virtual, upright, and reduced. Knowing this fact on test day will certainly save you some time. Question 2 asks us, what will happen to light that travels from a vacuum into a diamond? Take a second and pick an answer. The answer is C, because the index of refraction of a vacuum is less than the index of refraction of a diamond. When light travels from a low N to a high N, the light bends towards the normal. This third question asks us to calculate the index of refraction for a medium, given the critical angle. Take a second and pick an answer. The answer is B, and if we remember our equation for the critical angle, this question is a simple calculation. The index of refraction for a vacuum is 1 by definition. Putting our critical angle into the equation, we take the sine of both sides, and we find that n is equal to 2. Our final question asks us to find the object distance from a concave lens, given the image distance and the radius. Take a second and pick an answer. Our answer is A. Let's go through the steps to see how we solved this problem. The first equation we want to use is this one, that relates all those important distances. We can flip it around since we're solving for O and know image distance and radius. Radius is negative since we're dealing with a concave lens here, and image distance is negative as well since we're told that we have a virtual image. Let's fill out the math, and we get an object distance of 15 centimeters. If we look at the answer choices, we see that we still have to figure out which side the object is on. The object distance is positive, which means it's on the same side as the light coming in. But the best way to figure this out is to realize that a virtual image will also be on the same side as the light coming in. Our image is to the left of the lens, so our object must be on the left as well. Wow, we covered a ton of content in this video. To make sure you know what to focus on in your studies, let's sum up all the main points of geometrical optics. First, we covered the law of reflection, which said that the incident angle is equal to the reflective angle. Regardless of whether we get refraction or not, reflection is always happening. Speaking of refraction, we defined it as how light bends when it travels from one medium to another. The speed of this light changes as well, which we quantify with the index of refraction. The index of refraction is the ratio of the speed of light in a vacuum to the speed of light in a specific medium. Continuing with refraction, we analyze Snell's law, which helps us quantify how much light bends as it travels from one medium to another. At a certain angle, we get total internal reflection when no refraction occurs. Any angle greater than this critical angle will result in total internal reflection. We spent a lot of time analyzing spherical mirrors and lenses. Converging lenses were defined as making parallel light rays come together. Concave mirrors or convex lenses were identified as converging systems. In contrast, diverging systems cause parallel light rays to break apart. Convex mirrors and concave lenses were identified as diverging systems. The focal length of both spherical mirrors and lenses is defined as 1/2 of the radius of curvature. We interrelated focal length, radius of curvature, object distance, and image distance with this super handy equation here. You'll definitely want to be comfortable with this for test day. When image distance was greater than 0, we produced a real image. When image distance was less than 0, we produced a virtual image. And of note, plane mirrors always produce virtual images. We calculate magnification by taking the negative ratio of image distance to object distance, and if we have a negative magnification, our object is inverted. If the magnification is positive, our object is upright. If the absolute value of magnification was less than 1, the image is reduced, and if the absolute value of magnification was greater than 1, the image was magnified. Thanks for sticking with me through all that material. Be sure to come back and review the facts about geometrical optics so that you're totally prepared for test day. Good luck on your MCAT!